Okay, so this is the problem we were working on at the end of the last class period. And so we had gone in and we had entered that data. And then based upon the graph, we were able to see that it was increasing at an increasing rate, which tells us that there's exponential growth. And then we went to stat calc 0 and it gave us the initial value and the factor for our exponential equation. Because again, this is your initial value. And in this case, this is a growth factor. So that's where we were at when we left off. Okay, so part C says, what is the approximately yearly percentage growth? All right, so the language you're gonna need to pay attention to know what it's asking you to find is when it says percentage. So what is it asking us to find when you see that word percentage?
Rate.
The rate, thank you all, yes. So this means it wants us to find the rate. Okay, where is the rate located? Rate is R. And it's located within what? The factor. And in this case, we have a growth factor, right? So the rate can be found from the growth factor. So we know the growth factor from our equation to be, well, let me write this first. We know the growth factor is 1 plus R. And the value we found in part B for the growth factor was 1.490. But all we need is the R, right? So 1 plus what is this number? We'll just get rid of the 1. So we're going to look at this. So the percentage rate is 0.490. Move your decimal 2 places to the right. So that rate would be 49% or 49.0%. Either way you want to write it. If they continue to grow at the same percentage rate, what should Microsoft's revenue have been in 1996? Okay, what's given? So look at the top if you don't remember. Now, y'all, I just want to remind you, since we're talking about years, so whether it be notes, WebAssign, quiz, test, be careful because this one says years since 1989 and they just gave us 0, 1, 2, 3, 4. Some tables it might say 1989, 1990, 1991, and so forth. So you know if you were going to put those lists into your calculator, you need to do 0, 1, 2, 3, 4, but not the year. Okay, so be careful of that. All right, so the variable is T. So T equals, and is it T equals 1996?
No.
No, correct. We need to subtract the since 1989. So T is 7 years. Okay, so then to find the actual answer to the question, because it didn't want just the 7 years, but we need that. What am I going to do to actually find what their revenue is? So we're going to do R at 7 equals 0.785 times 1.490, and then we put 7 into that variable spot. So revenue 7 years after 1989, and then it's just a matter of putting it into your calculator. And I'm going to go 3 decimal places. Pay attention to WebAssign, test, quiz. If it doesn't say 2 is sufficient. 12.799. And what are we talking about here?
Revenue. Billions.
Okay, and how is the, what's the units of the revenue given in the table?
Billion.
Billions. A number I can't quite wrap my head around. Deal with billions too often. Assuming continued growth at the same percentage rate, when would Microsoft have revenue of $20 billion? So now we're given revenue, so now we are given what? The function value. And that is R equals 20 billion. All right, so if this is what's given, then when I substitute it into my equation, I'm gonna put it in place of the R. So we would have 20 equals 785 times 1.490 raised to the T. Okay, so how do we approach this problem to find out what T is?
Isn't that the Y1, Y2?
Correct. This is gonna be Y1. And this is gonna be Y2. And yeah, I've already got them in there. Guys, a little bit of time. I did this in my 9:30 class. Okay, so once we get those in, what do we do?
Window.
And, you know, I don't know, I always just leave it alone. I may have to come back to it. Ultimately, we want to be able to see what when we hit zoom 0. The intersection. So I may have to go back to my window, which is sometimes just a playing game. Shoot. Okay, mine came out all right. Can you guys see the intersection? Okay, I'm gonna go back to my window. For your X max, number 10 in there. And for your Y max, put in 45. And then hit zoom 0. See if that helps. Kind of basing it off of what my numbers were. Hayden, no?
It's just telling me invalid dimension.
Dimensions are is your window.
Looking back over it. They auto puts it back ahead of it.
Which is fun, because those were what my numbers were.
So I'm not sure what the issue is. So that. I have the plot one on.
All right, turn it off and then back on, see if that does it. If not, let's look at it after class.
All right.
Okay. So once you can see that intersection, now I need to find the values at this chair, the values at that intersection. How do we do that? Second trace or second calc, same thing. And then we want 5. And then this is where you hit enter, 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 and then you get the intersection. All right, so I'm gonna write down what it tells me is my intersection. And I get X equals 8.119. And I get Y equals 20. All right. We should know this is my variable and this is my function, right? It gave me the function, that's why those are the same. In relationship to this problem, instead of the letter X, what will I change that to? You can see up above that T is our variable, and that would be 8.119 years. And then I have to double check, is it asking me for how many years since 1989, or is it wanting to know the year?
One in the year.
It wants the year, so what I'm gonna do is take 1989 plus, and this is almost 8, so this is gonna be more like an approximation. So just pay attention to what I sign. Okay. All right, so that finishes exponential. That assignment is due tonight. And then the quiz that we're gonna take next week will only cover the first 2 sections. So this that we're getting ready to do will not be on the quiz that you take, okay? All right, we've been doing exponential equations. Now, the model we've been looking at was n equals p times a raised to the t power. That's when we were creating exponential equations, okay? In relationship to this unit, any equation that has an exponent is considered an exponential if the unknown is in the exponent. So they give us this general formula right here. I'm going to write it as 10 raised to the t equals x. So when this is written here, this is my variable, this is my function, okay? We just look at it this way because we want to look at its relationship to a logarithmic equation. And the logarithmic equation is written as log of x equals t. All right, there is a relationship between your exponential and your log equations. They are what we call inverses of each other. These are actually equivalent equations. One's just written in exponential form and one is written in log form. So one of the first things that we're going to look at is being able to take an exponential equation and rewrite it to its equivalent log and vice versa. We want to be able to go back and forth. Okay. All right. So let's think back to logs. I don't know if you've ever done log equations before. If you had, it maybe has been a while, but you actually have a log button on your calculator. It's to the left of 7. So we'll be using that. But your log equations are a particular base, like log base 5, log base 3. So they can be lots of different things. For purposes of this class and the calculator doesn't, this button here is not for all different bases. Does anybody know the general base for a log equation? 10 is correct. So good job. So in the calculator, when it says log, that means it's base 10. Okay, well, let's talk about our exponential equation, just what the math language is in this. We know t is an exponent, right? What is this number 10 called when it's connected with, it's the base, right? This log, if it doesn't show a number down here, what is it automatically understood to be? Log base 10. So this 10 represents that this log is log base 10. Okay. All right. We know that t is the exponent, right? So when I look at its relationship over here, I go, oh, a log is always equal to an exponent. So those are some helpful things that are going to make us be able to write them back and forth from each other. Okay. All right. So let's come down here to example 1 and look at what you're going to need to be able to do. Now, anytime you just see the word log without a base number written, it's understood to be base 10. Okay. So I'm going to go ahead and write it just to show you the easiest way to convert a logarithmic into its exponential. You always start here at the base and you go counterclockwise. So I would say, okay, I'm going to start with 10. So that's my base. raised to the exponent, and then that equals 100. So if I was going to rewrite this log into its exponential equation, it would look like this. And that's all it's asking me to do. And again, for purposes in this class, that will always be a 10. So if I'm going to rewrite it exponentially, this is log base 10. So it is also the base in my exponent. Logs are always equal to exponents. So this is my exponent, and then that would equal 1 over 1,000. So for both example 1 and example 2, just know that logs always equal the exponent. So logs always equal the exponent. Yep, it was my exponent. Logs always equal the exponent. Yeah, it's my exponent. Where having that memorized comes in handy is when you are given an exponential and it wants you to rewrite it as a log. So it wants me to rewrite it as a log. So I know I'm going to have log of something equals something. Okay, well, I can start eliminating numbers because if I remind myself that logs are always equal to the exponent, what is the exponent in this equation? -2. So this will be equal to -2. So I've used the -2. I'm not going to put it anywhere else. We know that this exponent of -2 has a base of 10. Well, logs that we're going to be dealing with are base 10. So this 10 would go down here. You don't have to write the 10 with a log if it's base 10, but if you want to, you can. Okay, so we've already used both of these numbers, so what's the only thing left? That goes right here. All right, here we know we're going to have log of something equals something. Okay, logs always equal the exponent. So this will equal what? This is base 10. I know this is base 10 whether I write it or not. So what's the only thing left? X. Now, I'm going to give you a couple of other examples of what you might encounter in WebAssign. I think this is like questions 1 through 5 in WebAssign that you might see things similar to this. It's going to ask you to like solve the equation. So you might be given something like this. Log of X equals 4. And then it's going to ask you to solve that. Well, if I had the number here, I could just go to the calculator, but I've got to figure out what this is, and I don't have a way to do it in my calculator. So what we're going to do is we are going to rewrite it as an exponential equation. Okay, so if I start with the log, I know this is base 10. So this is when we go counterclockwise. And so I know that 10 is my base, 4 is my exponent, equals X. I can go to my calculator and do 10 to the 4th. $10,000. Now, I could actually check my answer. We just said that this X is 10,000. So I'm going to go to my calculator and put in log of 10,000. And when I hit enter, what should it equal? Bam. All right, then an example that starts out with the exponential. So let's say we have 10 to the t equals 3. Well, I know 10 to the 0 is 1, 10 to the first power is 10. I have no idea 10 to what power is 3. So what that means is I'm gonna see if I can rewrite it as a log and if that would be helpful because it's base 10, so I can rewrite it as a log. Now, be careful here. Logs are always equal to the exponent, so what am I gonna put right here? T. T is your exponent. We know it's base 10, so I don't do anything else with the 10, so what goes inside my parentheses? Now, you'll have to read WebAssign. You can enter that as an answer, but if WebAssign says round to the nearest 3 decimal places, then it wants you to calculate this. So let's go ahead and calculate that. So if I did log of 3, and I'm gonna go 3 decimal places, so 0.477. So it just depends on how WebAssign wants it, so you're gonna have to pay attention to the directions. So what that means is we have found t, this exponent, to be approximately 0.477. So if I went to my calculator and did 10 raised to the 0.477, it should equal what? 3. Now, it won't be exact, right? Because we rounded it, but it will be very close to. And 2.999 is really close to 3. So we know we've done it correctly. Okay. All right. So what we've just been doing is working with what is called a common log, which is log of x, and it is always the power of 10, basically saying base 10. Okay. All right. That's what we call the common log. Now what we're going to look at is what is called the natural log, and LN represents natural log. Well, it's not power of 10, it is power of E. All right, y'all know pi, 3.14 and so on and so on and so on and so on. E is a number like pi. I think it's 2.78 and so on and so on and so on and so on. Okay, so it's kind of like pi, but so anytime you see natural log, just like when we see log of x, we automatically know that's base 10 if it doesn't have anything written there. Now when you see natural log of x, you go, oh, that's automatically a base of E. Okay, now here's why that's important, because we are going to rewrite this as a natural log. Now, before I do, I'm just gonna switch them. I'm gonna write natural log of 1 equals t. I'm just switching them. Here's the reason I did that. As soon as I see natural log, I know it has a base of E. So now to write it as an exponential, I can do my counterclockwise. And when it was written the other way, I can't do that as easily. So we would write this as E raised to the t power equals 1. So I'm going to rewrite and put the natural log on the left side. Again, as soon as I see the word natural log, I know I have base E. So to rewrite it, I do my counterclockwise. So I have E to the t power equals E. All right. Just like logs are always equal to the exponent, so are natural logs. Okay, so how do I know when I am gonna use log or I'm gonna use natural log? It's all about the base. Since this has base 10, that's why we rewrote it as a log. This has base E, so that means I would rewrite it as a natural log of something equals something. All right, well, it's always equal to the exponent, so this will be equal what? And this down here is an E, so both of those were used, so I just put X there. Natural log, whoops, didn't mean to do that yet. I know it's a natural log because it has base E. The exponent equal to -3, so that leaves this has to be X. Now, those were just general. Like my additional examples above, you may encounter some that you can actually calculate. So let's say we had natural log of X equals I don't like that I use that. Sorry, I'm looking, I'm like, I don't want to use that. I'm gonna say -4. All right, so if it wants me to find out what X is, I can't do this in my calculator. The only way I could do this in my calculator is if the number was here, but it's not. So what that means is I have to rewrite it. So again, I need to recognize that the base is E, and then I'm gonna rewrite it as an exponential. And I would get E to the -4 equals X. So then I could go to my calculator. Okay, now you gotta be able to find E. Anybody found it? All right, here's log, here's natural log. Right above natural log is E raised to an exponent. So since it's in blue, I would do second natural log, and the E is gonna pop up. And then I'm gonna put in, don't put in -4, put in -4 and hit enter, and I get 0.018. What did I say? 0.018. Now, again, I don't, whoops, that's supposed to be equal. I don't know which way that WebAssign wants it. If it doesn't say round to a particular number, then it's gonna want the exact answer, which would be E to the -4. If it says to round, then you'll go ahead and convert it to its decimal. All right. E to the T equals 3. Okay, well, I have no idea what number T is gonna be. So in order to find it, I can't work it as is. So what am I gonna convert this to? It's right now an exponential equation. We can convert it to what type of an equation? What is that called when it involves the E?
Natural log.
Natural log. So we're gonna convert it to a natural log. So I'm gonna convert it to a natural log. Now I need to fill in everything. Well, natural logs always equal the what? Exponent. And what is my exponent? T. I know the E is what is down here as my base. So what goes in here? And again, if it doesn't say round, then that's what you'll want to put in WebAssign. Or if it said round to say 3 decimal places, I would do natural log. Don't do second now. We want the natural log of 3. 1.099. It just depends on what WebAssign wants. So that means if I did do, whoops, oh, I hit the wrong button, obviously. Hit Y equals 0 second. To the 1.099, I should get a number very close to 3. can I do? Okay, all right. Now, base 10, there's something else that is used, base 10 is used, that we're gonna look at a little bit. Has to do with a Richter scale. Do you guys know what a Richter scale measures? Earthquakes. Yep, Richter scale measures earthquakes. You don't have this, but I want to give you an idea of what Richter scale, not scare. All right, Richter scales look like, okay? So obviously we know the higher the number, the bigger the earthquake, which means it shakes more. I think we can all agree on that, right? Okay, so we've actually had some earthquakes in Oklahoma before. And anytime we do, it's like people will get online and say, did you feel it? Well, wow, that was a big one, all that. And then like a News 5 or somewhere will come out and say, Enid experienced a 2.1 earthquake. Have you ever seen where they'll throw out a number? Okay, well, that number tells you the strength of it, okay? So the numbers they're talking to you about are these numbers down here. So obviously a 9 would be devastating, right? Or this building would probably no longer be standing, that large of an earthquake. Okay, well, 9 isn't just a 9. There's more to it than that. If you'll look at this vertical axis here, it tells us what it represents. So if we had one that measured a 9, then the strength of that earthquake is actually 10 raised to the 9th power. That is how strong the earthquake is. Right? So if I was comparing it to one that measured on a Richter scale of 8, that is still huge, but it's not just a difference of 1, right? That is 10 times stronger. So for every unit on the Richter scale, it is going up in strength by 10. Okay, so if I had say that we had an earthquake that measured a 5. So I'll say earthquake and it measured a 5, and then we have another earthquake and it measures a 3. This one is not 2 times as strong. That's not what it means, okay? 5 means 10 to the 5th, which would be 1, 2, 3, 4, 5. An earthquake of magnitude 3 would mean 10 to the 3rd, which is 1, 2, 3. 1, 2, 3, 4, 5, 1, 2, 3. Okay, so in essence, when they tell you these numbers, that's actually what in relationship to our problem? What piece is it? It's the exponent. So that magnitude that you see when it's a 2.1 or a 1.9, that means 10 raised to that power is the actual earthquake strength. So what we're going to be looking at is the difference. So if somebody said, oh, an earthquake of magnitude 5 and somebody else said 3, then I would want to think of that as the exponent, and I would go, oh, 5 minus 3 is 2. So it was 100 times stronger. Okay, so that's just kind of what a Richter scale looks like when you look at it on a graph. So before we got into the problems that we were doing, I wanted to go over that. Okay, so what we learned from that picture is that on the Richter scale, your magnitude is actually referring to your exponent when we have a base of what? 10. All of those were base 10. 10 to the 5th, 10 to the 3rd, 10 to the 9th. Okay, so Richter scale is base 10. But we know that those numbers are our exponents. And so we know it's base 10 to some exponent, and this tells us then the strength of that earthquake. So we're going to be doing a little bit of a comparison between some particular earthquakes, okay? All right, so let's take a look at example 1 and see how we'll approach this. So we have one earthquake that measures 5.5 on the Richter scale. So that would be like 10 raised to the 5.5. And we have another quake that measures 4.5. And it asks, how do they compare? Okay, well, the first thing that you want to do is you want to take the difference of their magnitude. So 5.5 minus 4.5 equals 1. So then what we know is to find how much stronger, we know that this is not 1 times stronger, but this is actually your exponent when you are talking about base 10. So this tells me that this earthquake is 10 times stronger. So if you had to explain that to me, then I would have that the 5.5 earthquake is, and how much stronger is it than the 4.5 earthquake? 10 times. So the 5.5 earthquake is 10 times stronger than the 4.5. Now, sometimes these numbers aren't always going to give you a, like this could be like 5.8 minus 4.5, so you might get like 1.3. So they won't always be nice, neat, whole numbers. Okay, so it won't always be 10 times stronger, 100 times. It might be 50 times stronger. Okay, so that can fluctuate. Now, if you'll notice in example 2, we're giving one of them of the Richter scale reading, but in its comparison, it is telling us that it is 1/1000th as strong. 1/1000th. How do I write that as a numerical number? Yeah, it has the th on the end. What's your place value? I had a decimal place. What's this first number?
100.
Tenths, and then, so I want 1/1000ths. So I have to go to the tenths, hundredths, thousandths, and I put a 1 there. So tenths, hundredths, thousandths. Or you could write it as 1/1000. Whichever way makes most sense to you, it doesn't matter. Okay, now here's the thing. This one, I had 2 Richter scales. I just subtracted them. That was my exponent and I was done. But now I have this situation. Okay, so let me think about this. So we have one earthquake and then I'll call this one another. Is this one stronger or weaker than this one? If I have a decimal, if I'm going the other way, this would be less strong because it's 1/1000. If it was 1,000 times stronger, it would be stronger. But when you have a fractional or a decimal, this one's actually less strong. Okay, all right, so here's what I know. On this another one, I'm going to look at its strength. So its strength is telling me it's 1/1000 or 0.001. You can put either of those two numbers there, it doesn't matter. And we know that the strength of an earthquake is found by 10 raised to some power. So think about it, it makes sense that this one's less strong because 10 to the first power is 10. This number's going smaller. Okay, all right, so I've got to figure out what 10 is. So on the prior page, when we had a base 10, what could we do that would help us find that exponent? We changed it to a log. So we are going to look at this as a log. So I know I'm looking at log of something equals something. Okay, and I know it's a log because it's base 10. All right, well, logs always equal the exponent. What's my exponent? T. So that means what number goes here? Nope, 10 goes down here because we're log base 10.
The 0.001.
So now I can go to my calculator and calculate that. Log 0.001 -3. So I get T equals -3. All right, now this is not your Richter scale reading here. What we're going to do is to find the Richter scale reading for that particular earthquake. So if you, what we had is, think about it. We're at 5.4 and it's telling us we're going to go -3, 1, 2, 3. So I don't know if that was helpful or not. Let me show you. So we have 5.4 is the one earthquake. And we're going to add that to the exponent of the other earthquake, which gives me 2.4. So this was the Richter scale reading for another quake. Which makes sense, because if you're at 5.4, then you're at 4.4, 3.4, 2.4, if you went -3. So it makes sense in relationship to that, okay? All right, we're actually going to stop there today. Somebody said yes.